This is Lab 5, the energy of a falling object. In this lab, we revisit some of the principles in Lab 2 of observing the motion of a falling object, except this time we use the knowledge acquired of the energy principle in order to analyze the motion and examine the energy of the system. So in this lab, we see that a ping pong ball falls a certain distance and is affected by gravity and the drag force. In Lab 2, we use Newton's second law in order to examine the object's motion. Newton's second law states that when a force is applied to an object, the object moves a certain distance with a changing speed. The change in that speed is affected by the sum of the total net forces acting on the system. In our lab, we see that the net forces acting on the system are the force of gravity, which is equal to the mass times gravity, and the drag force, which is the drag constant times the velocity squared. Once we know the exact finite number for the net force, we can find the change in the velocity, which we can use to find the change in the object's position. Incorporating what we know about the energy principle, we know that the change in energy is equal to the sum of the potential energies plus the sum of the kinetic energies. And since we know that energy must always be conserved, we can set this equation equal to 0. In our system, the change in kinetic energy is equal to 1/2 mv squared. Also in our system, the potential gravitational force, or the potential gravitational energy, is equal to the force of gravity times the distance h, or the height of the ball from the ground. We use the initial conditions of the object in order to model the motion and graph the energy to see if it's conserved. In our model, we see that the initial conditions are the mass equaling 0.027 kilograms, its initial position from the ground being, according to our axes, is equal to 0, negative 0.011, and 0. And since it's currently being held, we see that its initial velocity is equal to 0. We also know that the force is always equal to mg, and we find that B was experimentally found to be 0.00059. When we run our code, we not only model its motion, but we can also graph its energies, or the energy of the ball. The blue line represents the change in kinetic energy, and as we can see over time, the kinetic energy increases as the ball's potential gravitational energy, which is represented by the red line, decreases. Overall, the sum of the object's energies should be equal to 0. Therefore, we have justified that, or proven that, the energy principle is satisfied in our experiment.